There is a long, slow problem in physics. It has been quietly waiting for nearly 100 years, and tonight we are going to sit with it for a while. We are not going to solve it. No one has solved it. We are simply going to walk around it in the dark and consider what it might be. The problem is this. When astronomers look at the universe, at the way galaxies turn, at the way galaxy clusters hold together, at the faint patterned glow of the cosmic background light, they find more gravity than they can account for. There are not enough stars, not enough gas, not enough dust, not enough planets, not enough of anything they can see to explain how the cosmos is shaped. Something else is there. Something with mass, something that pulls, something that, by every measurement so far, does not glow, does not absorb light, does not scatter light, does not emit any signal we have learned to read. For lack of a better name, we call it dark matter. The word dark here does not mean black. It means simply that no light comes from it, and no light is bent by it, and no light is dimmed by passing through it. Light, as far as we can tell, ignores it entirely. It is invisible in the strongest sense of the word. Tonight is not a documentary about what dark matter is. We do not know what dark matter is. Tonight is a slow, patient thought experiment. The question we will sit with is this: what if the dark matter has its own physics? What if the part of the universe we cannot see is not made of one quiet kind of particle drifting alone, but of many kinds, with their own forces, their own light, their own chemistry? A whole hidden world running in parallel to ours, separated only by the fact that nothing in our world can quite touch it. This is a real, serious idea in theoretical physics. It has been written about in journals for decades. It has not been confirmed. Most of what we will say is hypothesis, conjecture, and careful guesswork. Each idea is one of many candidates, and any of them could turn out to be wrong. We will say so as we go. There is no urgency tonight. There is nothing here that needs to be remembered, nothing here that needs to be understood by morning. The universe will keep doing what it does in the dark, whether or not we follow along. So settle in. Let the lights go low. We will move slowly, the way one moves through an unlit room, feeling for the shape of things by their edges, knowing that some of what we touch may not be there at all. Begin with what we know. The universe, when it is weighed, comes out wrong. This is the oldest part of the story, and the part on which everything else depends. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster, a great gathering of more than 1,000 galaxies, hanging together in space about 320 million light-years away. He measured how fast the galaxies were moving relative to each other, and he found something strange. The galaxies were moving so quickly that, by the gravity of the visible matter alone, the cluster should have flown apart long ago. There was not enough mass to hold it together. Zwicky proposed that there must be additional matter in the cluster, matter that did not give off light. He called it, in German, Dunkelmaterei, the dark matter. For a long time, his idea sat at the edge of astronomy, considered curious, but not quite proven. Then, in the 1970s, an American astronomer named Vera Rubin, working with her colleague Kent Ford, looked carefully at how stars moved within individual spiral galaxies. They studied the Andromeda galaxy first, and then dozens of others. They expected to see what one sees in a solar system: stars near the center moving quickly, stars far from the center moving slowly, just as Mercury circles the Sun in 88 days, while distant Neptune takes 165 years. This is what gravity, applied to visible mass, predicts. Stars at the edge of a galaxy should drift, sluggish, almost trailing. That is not what Rubin and Ford found. They found that the stars at the edges of galaxies were moving just as fast as the stars near the center. The rotation curves were flat. The galaxies were spinning as though they were embedded in something much larger than themselves, something invisible, something that extended far past the bright spiral arms and held everything in a wide, gentle, gravitational embrace. The mass needed to explain this, they calculated, was at least 5 to 10 times the mass of all the visible stars. There was simply much more there than could be seen. This was the moment, more or less, that dark matter became part of the standard picture of the cosmos. It had been suggested. Now it was needed. Other lines of evidence followed, and they have only multiplied since. Light from distant galaxies bends as it passes near nearer galaxies, and the bending shows mass that no telescope has ever seen. In a place called the Bullet Cluster, 2 clusters of galaxies have collided, and the visible hot gas has slowed and pooled in the middle, while the gravitational mass, measured by how it bends light from objects behind it, has continued straight on through, in 2 great invisible clouds. The visible matter and the unseen matter have separated, like oil and water, and we can map them both. The unseen mass is there. It just does not interact much with anything else, most precisely of all, when we look at the cosmic microwave background. The faint warm glow left over from the very early universe, when the cosmos was only about 380,000 years old. We see in it a pattern of small temperature differences, tiny ripples in the heat. The exact shape of those ripples, measured now to extraordinary precision, tells us how much ordinary matter the early universe contained, how much dark matter, and how much of something else, called dark energy, that we will leave for another night. The numbers come out, again and again, the same way. About 5% of the universe is the matter we know. About 27% is dark matter. About 68% is dark energy. We are, by mass, a small minority report. Sit with that for a moment. The world we know, the planets, the stars, the gas between them, your body, the bed beneath you, the air in this room, is the small, bright crust on a much larger, darker substance. By weight, the universe is mostly something that has not yet been seen. There is a way of thinking about this that I find clarifying when I let it settle. The visible matter in the universe, the gas and dust and stars, the things our telescopes can see, is not arranged smoothly. It is not scattered evenly through space. It is gathered into a vast, sprawling pattern called by astronomers the cosmic web. The cosmic web is the largest structure in the universe. It consists of immense, near-empty regions called voids, often hundreds of millions of light years across, surrounded by sheets and filaments where matter has gathered. The filaments meet at nodes, dense knots where many threads converge. And at the nodes, often, sit clusters of galaxies, the largest gravitationally bound objects we know. Ordinary matter follows this pattern. Most of the visible mass of the universe, the galaxies, the gas between galaxies, lies along the filaments. Most of the visible volume of the universe is empty void. The pattern is real, repeated, and observable in great galaxy surveys. It is, when seen on the largest scales, a kind of three-dimensional lacework drifting through cosmic time. The cosmic web is not, in the standard picture, made by ordinary matter. The cosmic web is made by dark matter, and ordinary matter has settled along it like dew on a spider's threads. In the early universe, the small initial fluctuations in the dark matter density grew, under their own gravity, into the first wisps of structure. Ordinary matter, then in the form of hot ionized gas, was pulled toward those wisps. Over hundreds of millions of years, the wisps thickened into filaments, the filaments meeting into nodes, the nodes condensing into the first galaxies. The dark matter was the scaffolding. The visible matter, by gathering on top of it, made the scaffolding visible, but only indirectly, only by showing us where the unseen weight had already gathered. This is, I think, one of the most quietly remarkable things to know about the universe. The shape we see is not the shape that built the shape. The luminous galaxies are decorations on a structure that we did not, at first, know was there. Even now, when we map the cosmic web by counting galaxies, we are mapping not the dark matter directly, but the places where it has pulled the visible matter. The dark matter web is larger and more diffuse than the bright web that traces it. There are filaments that have not yet attracted enough gas to light up. There are dim threads stretching between galaxies, made mostly of unseen substance, that we know are there only because of how galaxies move along them. If the dark sector hypothesis is right, the cosmic web has another layer still. A dark layer, with possibly its own substructure, its own internal flows, possibly even its own analog of the way visible matter has gathered. This is conjecture. The standard picture of the cosmic web does not require it, but it is consistent with it in some forms. In any case, the basic image stands. The largest pattern in the universe is the dark matter pattern. The bright universe rides on it. Sit with that for a while. The galaxies you see in photographs of distant fields, the small bright smudges arranged in clumps and threads, those are not the structure. They are the markers. The structure is wider, vaster, mostly invisible. It has been pulling itself together slowly, since the universe was very young, and it will continue to pull itself together slowly, for as long as the universe has gravity. Now, for decades, the favored guess about what that something is has been a particle. A single, simple, very shy particle. The leading candidate has been called the WIMP, the weakly interacting massive particle. The idea is that dark matter is one kind of heavy particle, made in vast numbers in the first moments of the universe, and that it interacts with ordinary matter only through gravity and through the so-called weak nuclear force. The same force that governs certain, rare radioactive decays. If WIMPs exist, they would be passing through the Earth, through your bedroom, through your body, in great numbers right now. Estimates suggest the local density of dark matter near the Sun is roughly 0.4 of a gigaelectronvolt per cubic centimeter, which, if WIMPs are around 100 times the mass of a proton, would mean only a few of them in any given cubic meter of space. Sparse, quiet, almost never bumping into anything. For the last several decades, deep underground, in disused mines and tunnels, physicists have built exquisite detectors to try to catch a WIMP in the act of colliding with an ordinary atom. The detectors are made of liquid xenon, kept cold and clean, watched by sensitive light-detecting tubes, shielded against every form of stray radiation. They are remarkable instruments. They have looked year after year. So far, they have found nothing. The simple WIMP, the favored answer, has not appeared. Each experiment, when it reports its results, is described in the literature as consistent with no detection. A careful, scientific way of saying, we looked and there was nothing there to see. This is not, in itself, a crisis. The WIMP could simply be lighter or heavier or more weakly interacting than the next experiment can reach. There is still parameter space to search, but over time, as one detector after another reports the same gentle silence, theoretical physicists have begun, more and more, to ask a different kind of question. They have begun to ask whether dark matter must be one particle, whether it must be simple, whether it must be alone. And this is where tonight's thought experiment begins. Imagine, for a moment, that dark matter is not a single, shy particle drifting through space. Imagine instead that the dark sector, the part of the universe we cannot see, is rich. Imagine it has its own particles, its own forces, its own light, its own chemistry. Imagine it is, in its way, as full as our own world. The reason we have not detected it would not be that it is empty, but that it is hidden. A whole physics, parallel to ours, separated only by the thinnest possible membrane of non-interaction. Two worlds occupy the same space, never touching, except through gravity, which neither can refuse. This is the speculative idea we will spend tonight with. We will not prove it. We will only walk through it slowly and see what it might look like. There is a long, slow turning of the galaxies, somewhere above and around and through us. There is mass, holding everything together, that we cannot see. We have known about it for a long time. We have not yet learned its name. And so we begin. The first thing to notice, when one sits with the dark matter problem for long enough, is that the assumption of simplicity is just that, an assumption. It is not a measurement. It is not a deduction. It is a preference. When physicists first proposed dark matter, they preferred, naturally, to add as little new physics as possible. One particle, one mass, one weak interaction with ordinary matter. The simplest hypothesis that could fit the data. This is good practice. It is also, perhaps, a little arbitrary. The visible universe, the part we can see, is not made of one particle. The visible universe contains electrons and protons and neutrons, photons, neutrinos, an entire periodic table of elements built from those parts, and four fundamental forces governing how they all interact. The visible universe is, by any honest accounting, baroque, layered, full of unexpected structure. If 5% of the universe is this complicated, the thought experiment goes, why should we assume the other 27% is simple? In the literature of theoretical physics, this assumption of complexity is taken seriously. There are proposals, well-developed proposals, with mathematics, predictions, and ongoing simulations, that imagine the dark sector as a kind of mirror to the visible sector, with its own particles playing analogous roles to the ones we know. Models like this are called hidden sector models or dark sector models, and they are not the work of a fringe. They are written about in major journals, presented at major conferences, and tested, indirectly, against cosmological data. None of them has been confirmed. Some of them are inconsistent with current observations and have been ruled out. Others remain alive, waiting for better data. In the simplest version of these ideas, called atomic dark matter, one imagines that dark matter is made of two kinds of particles, one heavy and one light, oppositely charged under a force that is not electromagnetism, but is something like it. The heavy particle plays the role of a dark proton. The light particle plays the role of a dark electron. They are bound together by a kind of dark photon, which is to say, by a force carrier we cannot see, exchanged between them in the same way ordinary photons are exchanged between ordinary protons and electrons. The result in this thought experiment would be dark atoms, hidden hydrogen, a dark version of the most ordinary thing in the visible universe, a single bound pair of charges, quietly orbiting each other in a relationship that has nothing to do with us, and yet, in some strange way, mirrors something we already know. Stay with that image. Dark hydrogen, a pair of dark particles drifting through the cold space between galaxies, bound by a force we cannot feel, exchanging photons that no telescope can see. They would not glow. They would not warm anything. They would simply be there in their own quiet pairings, doing nothing that we are equipped to notice. There could be many of them. There could be uncountably many. This is what is meant by a hidden sector, not a place far away, but a layer of physics laid over the same space we live in, untouched and untouching. It is, for now, only a hypothesis. There is no experiment that has ever directly seen a dark atom. There may never be one. But the mathematics is consistent, and the consequences are interesting enough that serious people have spent years working out the details. We will spend the next several hours with those details, gently. There is no rush. The universe has been keeping its secret for 14 billion years. It can wait a little longer. The atoms of our world, ordinary atoms, have a peculiar history. They were not always atoms. In the first hundreds of thousands of years after the Big Bang, the universe was too hot for atoms to hold together. The protons and electrons that would, eventually, settle into hydrogen were instead a hot ionized plasma, drifting through a fog of light. The plasma and the light were locked together, scattering off each other in countless tiny collisions, oscillating like a fluid. Only when the universe expanded enough to cool below about 3,000 degrees did the protons and electrons finally find each other and settle into neutral hydrogen, releasing the light. That release is what we now see, 14 billion years later, as the cosmic microwave background. The faint, warm glow of the universe is finally letting go of its first photons. In the atomic dark matter hypothesis, something similar might have happened in the dark sector. There would have been a dark plasma, dark protons and dark electrons, hot and ionized, oscillating with their own dark light. As the universe expanded, the dark sector cooled too, and at some point in this thought experiment, dark recombination occurred. Dark electrons fell into orbit around dark protons. Dark hydrogen formed, and the dark light was released into a faint, never-detected dark cosmic microwave background, glowing with a brightness no instrument can measure, in wavelengths we have no way to read. This is, again, all conjecture. The numbers depend on assumptions about dark masses and dark coupling strengths that are not measured. But the picture is consistent. If dark matter is atomic, then somewhere out there, perhaps everywhere out there, there is a dark afterglow from a recombination that happened alongside our own. Two parallel histories, two parallel coolings, two parallel releases of light, neither of them able to see the other. There is, in this picture, a particular detail worth lingering on, because it tells us something about why these models are not arbitrary. In the literature, one of the cleanest ways to write down an atomic dark matter model is to start with a hidden gauge symmetry, a kind of dark electromagnetism with its own coupling constant. In our world, the coupling strength of electromagnetism, the so-called fine structure constant, is approximately 1 over 137. This number determines, among other things, how tightly electrons are bound to protons in ordinary atoms. It determines the size of an ordinary atom, the energy levels of its bound states, and the wavelengths of light it emits and absorbs. Our world is, in a quiet way, shaped by that small dimensionless number. If a dark sector exists, with its own analog of electromagnetism, the dark fine structure constant could in principle be any value at all. It might be much larger, in which case dark atoms would be much smaller and more tightly bound than ours. It might be much smaller, in which case dark atoms would be larger and more loosely bound. The mass scales of the dark proton and dark electron could be anywhere across many orders of magnitude. Each combination produces a different dark physics, with different timing for dark recombination, different rates of dark molecule formation, different cooling efficiencies, and different patterns of small-scale structure. What this means is that the dark sector, if it exists, has a free parameter space. It is not one specific theory, but a family of theories, parameterized by a handful of unknown numbers. Cosmological observations constrain those numbers. The Planck satellite measurements of the cosmic microwave background, in particular, place tight limits on how much energy could have been in a dark plasma at certain epochs. The matter-power spectrum, derived from galaxy surveys, places limits on how strongly the dark sector could have suppressed structure at small scales. The combined constraints carve out the region of parameter space in which an atomic dark matter universe could still be consistent with what we see. That region is not empty. There remain bands of possible dark fine structure constants and dark mass ratios in which the universe could contain a substantial atomic dark matter component, while still looking on the scales we have measured. Very much like the universe we observe, the bands are tighter than they used to be. They will be tighter still in the next decade. So the picture is not that dark matter is whatever we want it to be. The picture is that the dark matter hypothesis is being narrowed slowly from many directions, but the narrowing has not yet excluded the rich possibilities. The simple picture, in fact, has been narrowed too, from a different angle, by the failure of direct detection. The two narrowings have been happening in parallel, and where they leave us is roughly here. Simpler models are increasingly disfavored, richer models are increasingly contemplated, and the data continues to come in, year by year. There is a quietness to this idea that I find difficult to express in words, and so I will not try too hard. Two universes of light, occupying the same space, neither aware of the other. The night sky as we know it, full of stars and galaxies, would be one of two such skies. The other would be glowing, just as faintly, in light that no eye in our world will ever see. It would be there now. It would have been there when the dinosaurs were alive. It would have been there before the Earth formed. It would still be there long after the sun has died. This is, of course, only an idea. The dark sector might be nothing like this. It might be much simpler, or much stranger, or might not exist as a separate sector at all. We will not know unless one of the next generations of experiments finds something. And even then, what we find will likely be only a small piece of a much larger puzzle. What matters for tonight is not the truth of the picture, but the kind of picture it is. A picture of complexity, a picture of richness, a picture of a universe in which there is more, rather than less, than we have yet seen. The favored simple particle has not been found. The detectors keep running. The data keeps coming back the same. And in the quiet space left behind by the absence of WIMPES, a different kind of question has begun to take root. What is the dark matter particle? But what is the dark world like? That is the question we will sit with tonight. We will not answer it, but we will let it turn slowly in the dark. Now consider the matter of forces. In our world, we know of four fundamental interactions. There is gravity, which holds you to the Earth and the Earth to the Sun. There is electromagnetism, which makes light and binds electrons to atoms. There is the strong nuclear force, which holds the quarks inside protons and neutrons, and binds protons and neutrons together into atomic nuclei. And there is the weak nuclear force, which is responsible for certain kinds of radioactive decay, and which played an essential role in the early universe in determining how many protons and neutrons survived. Four forces. They appear on close inspection to be the entire repertoire of nature. But this is, again, an inference from what we can see. 5% of the universe operates under these four forces. The rest of it might operate under more. There might be additional forces, hidden in the dark sector, governing particles we cannot detect, with mediators we cannot directly observe. In the literature, these hypothetical force carriers are sometimes called dark photons, and the forces they carry are called dark electromagnetism, or, more cautiously, hidden sector forces. The term dark photon does not mean a black photon or a sad photon. It means a particle that mediates a force in the dark sector, in roughly the way the ordinary photon mediates electromagnetism in ours. If dark photons exist, and this is a hypothesis, only then the dark sector would have its own kind of light, not visible to us, not detectable except possibly through a tiny bridge. In some models, the dark photon is allowed to mix slightly with the ordinary photon, in a way physicists call kinetic mixing. The mixing, if it happens, is extremely small. It would mean that, very rarely, a dark photon could behave a little like an ordinary photon, or an ordinary photon could behave a little like a dark one. Experiments are searching for this effect right now. They have not found it. They have only set limits, telling us how small the mixing must be, if it exists at all. But suppose the mixing is just large enough to be real, but small enough to have escaped notice so far. Then there would be the faintest possible coupling between the visible world and the dark world. Almost everything would still pass through unchanged. Dark matter would still be invisible, almost, but here and there, in a deep enough detector, with enough patience, the dark world might leave a trace. This is one of the reasons the experiments continue. Not because anyone is sure the WIMP is there, but if the dark sector has its own physics, then the bridge between worlds may be very small, but not zero. And every year of running, every additional ton of liquid xenon, every additional season of careful watching, lowers the limits a little further. Eventually, the experiments will reach a point where they cannot distinguish the dark sector from the background of ordinary neutrinos arriving from the sun. That boundary is called the neutrino floor, and it is, in some sense, the floor below which a passive search cannot go. We are not there yet. We are getting closer. There is a kind of patience to this, a kind of long, careful, undramatic patience that I think is one of the most beautiful things about modern physics. The experiments are not searching for proof in any single moment. They are slowly narrowing the dark. Each year, the space of possibilities shrinks. Each year, the kinds of dark matter that are still allowed grow a little stranger, a little less like the simple guess we started with. This is not failure. This is what learning looks like when the thing you are learning about does not want to be seen. Sit with that as we move on. The universe is being narrowed slowly by people in white coats in cold rooms underground, and most of them will never have anything dramatic to report. They will only have the next year of data, slightly better than the last, and they will offer it to the world without flourish and continue. In the dark sector hypothesis, the dark photon is one possibility among many. There may also be heavier dark force carriers, called by names like dark Z bosons or dark Higgs bosons, by analogy with the bosons we know. Some of these are predicted by certain theoretical frameworks, including some extensions of supersymmetry and some string-theoretic models. None of them has been confirmed. Some of them are starting to be ruled out. Others remain open. What is interesting, again, is not the specific names. What is interesting is the texture of the picture. If dark matter has its own forces, then dark matter can do things. It can cluster. It can bind. It can radiate. It can, in some models, even cool. And this is where the picture begins to grow strange and beautiful, and where we will spend much of the rest of the night. Cooling is one of the most ordinary things in the visible universe, and yet it is the secret of almost everything we love. A cloud of hydrogen gas in interstellar space is hot and diffuse. It cannot collapse because the heat pushes it outward as fast as gravity pulls it inward. But hydrogen radiates. It emits photons slowly in particular wavelengths, and as it emits photons, it loses energy. The cloud cools. As it cools, gravity gains the upper hand, and the cloud begins to contract. It contracts slowly over millions of years until, at the center, the density and temperature are high enough to ignite a star. Without cooling, no star would ever form. Without stars, no planets. Without planets, no us. The visible universe is structured the way it is, in part, because ordinary matter is dissipative. It can give up its energy in the form of light, and what is left behind condenses. Dark matter, in the standard picture, does not cool. It does not radiate in any way we can detect. It sits in vast, diffuse halos around galaxies, never falling into a smaller, denser shape, because there is no mechanism for it to lose its energy. A halo of standard cold dark matter is roughly spherical, vast, and slow. It does not condense into stars. It does not condense into anything. But in the atomic dark matter picture, this might not be quite true. If dark matter has its own forces, it might also have its own way of radiating. In the literature, this is called dissipative dark matter. The idea is that dark particles, like ordinary particles, can collide and emit dark photons, and in doing so lose energy. Over time, a halo of dissipative dark matter could cool. It could fall inward. It could form denser structures. It could, in principle, form a thin disk, embedded inside the disk of a galaxy, parallel to the visible disk but invisible. This idea was developed in detail in a series of papers about a decade ago by physicists, including Lisa Randall and her collaborators. They called the model double-disk dark matter. The hypothesis is that most of the dark matter in a galaxy might still be in the diffuse halo, the way standard cold dark matter is. But a small fraction, perhaps a few percent, might have its own dissipative interactions, and might therefore cool, and form a thin pancake of dark matter lying within the visible galactic disk. It would be there now in our galaxy, parallel to the plane of the Milky Way. We would not see it. We would only feel, possibly, its gravity. There is, as of this writing, no confirmed evidence for a dark disk in the Milky Way. The constraints from stellar motions are getting tighter all the time. If a dark disk exists, it must be subtle. But the idea has not been ruled out, and serious efforts continue to look for its signature in the kinematics of nearby stars. If it does exist, the picture is striking. Imagine the Milky Way as we see it now, a slow spiral, 100,000 light-years across, with 200 billion stars arranged in a flattened disk. Now imagine, sharing the same plane, a second disk, made of dark atoms, dark molecules, possibly even darker structures. It would be thinner than the visible disk, thinner, because dissipation is more efficient for the dark sector in some of these models. It would rotate. It would, in some models, contain its own substructure. We would pass through it every night as the sun bobs slowly above and below the galactic plane. We would never know. I want to slow down here for a moment, because this is one of the most beautiful images in modern speculative physics, and it deserves a slow look. Two galaxies occupying the same space, one bright, full of stars and gas and human eyes, pointed up at it. The other invisible, made of matter we have not learned to see, does its own quiet work in the dark. Neither knows the other is there. Both contribute to the gravity that holds the whole thing together. Both turn at the same rate, in the same sense, around the same center, for the same reason. It is not the universe we expected. It is not necessarily the universe we have. But it is the universe we cannot yet rule out. And so we keep walking in the dark. Now consider what dark matter would be made of if these atomic models are right. Not protons and electrons exactly, not the ones we know. The dark proton in these models is a heavy fermion, a particle with mass somewhere in a wide allowed range, perhaps similar to the proton, perhaps much heavier or lighter. The dark electron is a lighter fermion, again with mass somewhere in a broad allowed band. They are not specifically related to ordinary protons and electrons in any way that we can pin down. They are simply the names we give, in this thought experiment, to the heavy and light constituents of a hidden two-particle bound state. The bound states themselves might be simple, like dark hydrogen, or might be more complicated. There is recent theoretical work, published, peer-reviewed, that has begun to explore what happens if dark matter is rich enough to support its own chemistry. Not just dark atoms, but dark molecules. Not just isolated bound pairs, but dark hydrogen-like molecules, which is to say, two dark atoms sharing dark electrons in a kind of dark covalent bond. The mathematics is built by analogy. The reaction rates are estimated by rescaling the rates that govern ordinary hydrogen molecule formation. The work appears in papers with names like molecular chemistry for dark matter, and it is a careful, modest, technical effort, not a grand pronouncement. The authors are not saying that dark molecules exist. They are saying that, if the parameters of the dark sector fall in certain ranges, then the dark sector would have its own chemistry, and that chemistry would have observable consequences for the way dark structures form on small scales. What sort of consequences? Well, in the visible universe, hydrogen molecules can cool more efficiently than hydrogen atoms can at certain temperatures. Molecular cooling is one of the mechanisms by which the very first stars are thought to have formed in the early universe. Without molecular hydrogen, the first stars would have been different, heavier, fewer, slower to ignite. Cooling controls structure. In the dark sector, the same might be true. If dark molecules form and cool, then dark gas can collapse into smaller structures than dark atoms alone would allow. Smaller halos. Smaller, denser regions. Possibly even objects analogous to compact stars in some models, though this is at the very edge of what current theory considers, and many of these scenarios are already constrained by observations. There is, hovering at the edge of these papers, an idea that I think deserves a quiet hearing because it has a particular kind of strangeness to it. If the dark sector has its own chemistry and its own cooling and its own dissipation, then, in principle, the dark sector could form its own bound structures, its own clouds, condensing inward, its own dense cores. In some extreme models, even its own dark stars and dark black holes, formed by mechanisms parallel to but separate from the ones that formed our own. I want to be careful here. This is the most speculative ground in tonight's walk. Most theorists would say that current observational constraints make it difficult for very large fractions of dark matter to be highly dissipative. Because such matter would have already collapsed into structures we would have noticed by their gravitational effects. The double-disk model gets around this by making the dissipative component a small fraction of the total. The strict atomic dark matter models get around it in other ways. There is no consensus picture. There is only a landscape of ideas, each consistent with different choices of parameters, each with its own observational signatures, most of which have not yet been seen. What we are doing here is sitting with the landscape, letting it spread out before us, walking through it slowly, not committing to any single map. The night is long, the universe is patient. The dark, whatever it is not going anywhere. There is a phrase that recurs in the literature on these models. The phrase is dark sector richness. The dark sector might be rich. It might not have just one particle but many. Not just one force but several. Not just structure but structure within structure. A hidden world as full as our own. And then there is the deeper phrase, the one that lies underneath all of the others, and that I think is the real subject of tonight's thought experiment. The phrase is symmetry breaking. The dark sector, if it exists, would have its own version of the same physical symmetries that govern our own. Some of those symmetries might be unbroken, in the dark, while in our world they are broken, leading to a different set of stable particles, a different set of binding energies, a different set of allowed structures. Some of the symmetries might be broken in the same way, leading to a dark sector that mirrors our own almost exactly. Some might be broken differently, leading to a dark sector that resembles ours only loosely, with different ratios, different mass scales, and different dominant kinds of bound state. Each of these possibilities is its own theory. Each makes different predictions. Each has, so far, neither been confirmed nor ruled out completely. Each, if true, would imply a particular shape to the invisible part of the universe. It is, perhaps, the most quietly enormous question in modern physics. What is the geometry of the dark world? We do not know. We may not know for a long time. Tonight, we are simply walking through the question in the soft way that these questions allow themselves to be walked through. There is nothing to do. There is nowhere to be. The universe will keep its secret a little longer. So far, we have been speaking mostly about what is called atomic dark matter. The proposal that dark matter, like ordinary matter, is made of charged constituents bound together by a force similar to electromagnetism. There are other proposals, equally serious, with different shapes. We will not survey all of them tonight. That would take many nights, and we are not in any hurry. But we should pause to mention a few more so that the picture is honest. One proposal is called mirror matter. It is, in some ways, the most beautiful of the dark sector ideas, and also one of the oldest. The idea goes back to the 1950s and 60s, when physicists noticed that the weak nuclear force, alone among the four forces, distinguishes between left-handed and right-handed particles. Most of nature is symmetric. The weak force is not. Some physicists, troubled by this, proposed that for every left-handed particle in our world, there might exist a corresponding right-handed mirror particle in a parallel sector, restoring the overall symmetry of nature. The mirror sector would be a complete copy of our own particle physics, with its own mirror protons, mirror electrons, mirror photons, mirror nuclei, mirror chemistry. It would interact with our world only through gravity, and possibly through a tiny mixing of photons with mirror photons. Mirror matter in this picture is a candidate for dark matter. The same kind of stuff we are made of, only flipped, hidden, sharing the universe with us in a kind of perfect, untouching parallel. The mirror matter picture has been studied for decades. It is mathematically elegant. It is consistent with some, though not all, observations. It is also, like all the other dark sector hypotheses, unproven. There are constraints on how much the visible and mirror sectors can interact, and those constraints are tight enough that some of the original versions of the theory have had to be modified. The current versions remain alive, but speculative. There is, again, a particular feeling that comes with sitting with the mirror matter idea for a while. The feeling is one of perfect parallel structure. Two periodic tables, two sets of stars, two histories of how matter cooled and clumped and assembled itself, two trees of complexity. It is not promised by the data. The data is consistent with much simpler dark matter, but the idea has not been ruled out, and it is, for whatever it is worth, the fullest version of the dark sector hypothesis. The richest, the one in which the universe is, in a sense, twice itself. Another proposal, very different, is called self-interacting dark matter. The idea here is more modest. It does not necessarily require a mirror sector or atomic structure. It only requires that dark matter particles, whatever they are, interact with each other through some force, with a strength somewhere in a particular allowed band. The motivation comes from observations of the inner cores of dwarf galaxies and galaxy clusters, where the standard collisionless cold dark matter picture predicts cuspy density profiles, sharp peaks in the dark matter density at the very center, while observations sometimes seem to favor flatter cores. If dark matter particles can scatter off each other, even occasionally, they can transfer energy in their inner regions, smoothing out the cusps and producing the observed cores. Self-interacting dark matter, in this sense, is one of the more conservative dark sector proposals. It does not require a whole hidden world. It only requires that the dark matter is not perfectly collisionless. The simplest models posit a single light-dark force carrier, sometimes a dark photon, sometimes a different kind of mediator, exchanged between dark particles. The cross-sections required to fit the observations are roughly 1 square centimeter per gram, give or take. This is large by particle physics standards. It is small by visible matter standards. It sits in a peculiar middle band that has, so far, not been excluded. Whether the small-scale anomalies that motivate self-interacting dark matter are real, or whether they are artifacts of how baryonic physics, the physics of the visible matter, disturbs dark matter halos, remains a matter of ongoing debate. The picture is not settled. It is one of those frontier areas where the data is suggestive, but not yet decisive, and where reasonable people working in the same field can hold quite different views. There is also the axion. The axion is a hypothetical particle, much lighter than the WIMP, originally proposed in the late 1970s for reasons having to do with a different problem in particle physics, called the strong CP problem. It would be much lighter than an electron, possibly much lighter than a neutrino, and it would interact extraordinarily weakly with ordinary matter. If axions exist in great enough numbers, they could provide the dark matter. They are not, in the strict sense, a dark sector. They are a single particle like the WIMP, but a different kind of single particle, light and wave-like, rather than heavy and particle-like. Axion dark matter has its own dedicated experiments and its own slowly narrowing space of possibilities. There are also primordial black holes, small black holes that might have formed in the very early universe, before any stars existed, and that might still be drifting through space today, providing some or all of the dark matter through their gravity alone. The constraints on this idea are now quite tight in many mass ranges, but small windows remain in which primordial black holes could still be a substantial fraction of the dark matter. There is yet another way of dividing up the possibilities, which physicists sometimes call the temperature spectrum of dark matter. The terms can be a little misleading, so let me explain them slowly, since we are not in any hurry. When physicists call dark matter cold, they do not necessarily mean that it is, in some absolute sense, at a low temperature. They mean that, by the time it began to gather into structures, its particles were moving slowly, compared to the speed of light. Cold dark matter sinks easily into gravitational wells. It clumps on every scale, small clumps, larger clumps, clumps within clumps, all the way down. The standard cosmological model, the one called lambda CDM, assumes cold dark matter as its default. The model fits an enormous range of observations, from the cosmic microwave background to the distribution of galaxies on the largest scales. It is the most successful single hypothesis we have. Hot dark matter, in contrast, would be made of particles moving close to the speed of light when structure formation began. Such particles cannot easily gather into small clumps. They free stream past potential structures, smoothing things out before structures can form. Hot dark matter alone cannot account for the observed universe. The small galaxies we see today would not, in a hot dark matter universe, have had time to assemble. Neutrinos, which we know exist and have small but non-zero masses, are a known component of hot dark matter. But they are too few and too light to provide the bulk of the dark matter. The data simply rules it out as the dominant component. In between, there is the possibility of warm dark matter. Particles are a little warmer than cold, a little colder than hot. They would suppress the formation of the very smallest structures, while allowing larger ones to form normally. Possible candidates for warm dark matter include hypothetical particles called sterile neutrinos, with masses in the keV range, or axions produced in particular ways. There are observational constraints on warm dark matter, mostly coming from the very thin gas between galaxies. A structure called the Lyman alpha forest, observed in the spectra of distant quasars. The forest is sensitive to small-scale structure in the early universe. If dark matter were too warm, the forest would look different from what it does. Current data suggests that if dark matter is a thermal relic, its mass must be at least a few kiloelectronvolts. The constraint tightens with each new survey. What I want to point to in mentioning all of this is that even the question of the temperature of dark matter, a single, basic, physical property, is not resolved. We do not know whether the dark matter is fully cold, slightly warm, or whether different components of it have different temperatures. The dark sector hypothesis we have been walking through tonight is, in some forms, a hypothesis about exactly this: the idea of a multi-temperature universe, in which the dark sector and the visible sector have different temperatures, with their own thermal histories, is taken seriously in the literature. The mathematics has been worked out. The cosmological consequences have been calculated. The thing has not been measured. There is something curiously personal about the thought that the dark sector might have its own temperature. Temperature in physics is a measure of the random motion of particles, the wiggle of things. A higher temperature means more wiggle. A lower temperature means less. If the dark sector has its own temperature, it has its own scale of wiggle, separate from ours. It might be wiggling faster than we are. It might be wiggling more slowly. It might be at a temperature far below the cosmic microwave background, in which case it would be, in a real sense, colder than the cold of empty space, almost absolutely still. It might be at a temperature above ours, in which case its particles, even today, would be quietly moving more energetically than ours. We do not know. There is no measurement. There may not be one for a long time, but the picture, even unconfirmed, is interesting. The same room you are in, the same cubic meter of space, might contain visible matter at one temperature and dark matter at quite another. The two not in thermal contact, doing their separate slow things in the same place, neither warming nor cooling the other. It is not how we usually think about a room. It is, perhaps, how the universe actually works. Now let us walk for a while along yet another path. There is, in the modern study of dark matter, a long-running set of observations that may or may not be telling us something. The observations are made of small galaxies, dwarf galaxies, the smallest galaxies that exist, and of the inner cores of larger galaxy clusters. The questions are technical, but the underlying issue is this. Standard cold dark matter, with no self-interactions, predicts a particular shape for the distribution of dark matter in these small structures. It predicts, in particular, that the density of dark matter rises sharply at the very center, what physicists call a cuspy profile. The density goes up and up, peaking in a sharp inner peak. When we look at the actual rotation curves of certain dwarf galaxies, the dark matter distribution they imply does not always look cuspy. Sometimes it looks chord, flat in the middle, with a relatively constant density across the inner regions. The data is noisy, the analysis is difficult, and there are many ways that ordinary matter physics, the so-called baryonic feedback from supernova explosions and stellar winds, could plausibly turn an originally cuspy profile into an apparently chord one. So the discrepancy is not a crisis. But it has been there, in various forms, for a long time, and it is not fully explained. There are similar puzzles regarding the number of small satellite galaxies orbiting the Milky Way. In simple cold dark matter simulations, the number of small subhalos predicted is much larger than the number of small satellite galaxies actually observed. This is sometimes called the missing satellites problem. It can be explained by the fact that not every dark matter subhalo successfully forms a visible galaxy. The smallest ones may simply be too small to ignite stars. There is also a related issue, called the too big to fail problem, in which the simulations predict subhalos too massive and dense to remain dark, and yet the corresponding bright galaxies do not seem to be present. These are not, by themselves, evidence for new physics. They are anomalies, places where the simple model does not quite fit, and where the explanation could lie either in the complicated physics of how visible matter and dark matter interact during galaxy formation, or in something genuinely new about the dark matter itself. One of the motivations for self-interacting dark matter, and for some of the dissipative dark matter models, is precisely that they could potentially smooth out these small-scale tensions. They predict slightly different small-scale structure, with naturally chord profiles and slightly different abundance of small halos, and the predictions can, in some parameter ranges, fit the data better than the simple collisionless cold dark matter does. Whether the small-scale tensions will eventually be resolved by better baryonic physics, or whether they will turn out to require new dark matter physics, remains an active research question. The honest answer is that we do not know. The simple model still works very well on large scales. The tensions are small and contested. The work continues. What I find moving, when I sit with this for a while, is how subtle the case for new physics has to be. We are not looking for a giant flaring signal. We are looking for tiny inconsistencies in the distribution of stars in the smallest galaxies, in the spectra of light from the most distant quasars, and in the shape of the cosmic background radiation at very small angular scales. The dark sector, if it has its own physics, would mostly leave the standard picture intact. It would only show up if it shows up in the corners. There is something almost monastic about this. The work of slowly, carefully looking in the corners, of measuring the same things to ever greater precision, of running the same simulations with finer and finer resolution, of asking, year after year, whether the small tensions are getting larger or smaller, whether they are real or artifacts, whether they require new physics or only a better understanding of old physics. It is the work of patience. It is, in a sense, the work that builds science. And it is happening right now in offices and computer clusters and observatories around the world, while you and I are in this dim room together, walking through the question. There is also a different kind of proposal we should mention briefly. This is a proposal that goes by the name of fuzzy dark matter, or sometimes wave dark matter. The idea is that dark matter might be an extraordinarily light boson, so light that its quantum wavelength is comparable to galactic scales. Such a particle would not behave, on those scales, like a normal particle. It would behave like a wave. It would have a coherent, rippling structure on the scale of small galaxies, and this rippling could, in principle, smooth out the inner cores in ways consistent with what we observe. The masses required are extraordinarily small, perhaps 10 to the minus 22 electron volts, which is something like 10 to the negative 31 times the mass of a proton. This is a regime of physics that is, by any normal standard, deeply strange. But it is, again, a serious proposal with dedicated theoretical work and observational constraints. What I am trying to convey, by listing all of these possibilities, is the breadth of the current open landscape. The dark matter could be any of a dozen quite different kinds of things, and physicists have, over the last several decades, taken each of them seriously enough to compute its consequences in detail. We are not, when we say we do not know what dark matter is, being modest. We are stating a precise truth. The space of viable hypotheses is large, and the data so far have not, despite enormous and patient effort, narrowed it to a single answer. This is, I think, an honest and rather moving place to be, intellectually. We have learned enough to know that something is there. We have not yet learned enough to know what. We are in the middle of a question that is older than any of us and likely to be older than our children's children. We are doing what we can. We are leaving the question slightly clearer for the next generation. That is enough. Each of these is a real proposal. Each has its own literature. None has been confirmed. What is striking, looking across the whole landscape, is how many doors remain open. It is sometimes said, in popular accounts, that dark matter is one of the great failures of modern physics, that we have been searching for it for decades and have not found it. This framing is, I think, not quite right. What we have done over the last several decades is not to fail to find dark matter. What we have done is to learn, with increasing precision, what it cannot be. The space of allowed possibilities has shrunk. The kinds of particles that might play the role have been narrowed. The rough mass ranges, the rough interaction strengths, the rough abundances. These are constrained in ways they were not, even 10 years ago. The search has progressed. It has simply not yet ended. And the more it progresses, the more interesting the surviving possibilities become. The simple picture has had to give way slowly to pictures that are richer, stranger, and more layered. A dark sector with its own chemistry, a mirror world, a halo with its own dissipative subcomponent. These are not desperate guesses. They are the next class of ideas, the ones being taken up by serious theorists as the simpler ones are, one by one, set aside. We are, in some real sense, in the middle of a long, slow shift in how physicists think about what most of the universe is. The shift will continue. We do not know where it will end. We may not know in our lifetimes, but we are, at the very least, learning something. Even when the answer is that the simple answer is wrong. Take a slow breath now, if you are still with me. The universe has been keeping its secret for a long time. It has been keeping it through the lives of every person who has ever wondered about it. It will keep it a little longer. There is no harm in not knowing. There is no harm in walking, in the dark, around a problem that does not solve itself. That is what we are doing. That is, in a sense, what we have always been doing. Let us keep walking. One of the things that draws me to the dark sector hypothesis is the way it changes one's sense of what space is. We are used, perhaps without thinking about it, to imagining space as something nearly empty, with matter scattered through it sparsely. A few molecules of gas per cubic centimeter in the better neighborhoods, and far less than that elsewhere. The universe, in our usual picture, is mostly nothing. A great cold vacuum, lit here and there by stars. But the dark matter calculations tell us that, even where there is no visible matter, there is still substance. Even in the empty room around you, there are dark matter particles passing through. Even in the deepest interstellar void, there is dark matter. Even in the great voids between galaxy clusters, where ordinary matter is at its most diffuse, there is dark matter, holding the cosmic web together with its gravity. Space is not empty. Space is full of something we cannot see. If the dark sector hypothesis is right, this fullness is even greater than we have so far supposed. There would not just be dark matter in the form of one drifting particle. There would be dark photons, dark forces, dark atoms, possibly dark molecules, and possibly dark structure. The universe would not be a sparse arrangement of bright objects in a dark void. The universe would be a thick, layered, mostly invisible medium, with bright objects floating in it like islands. The thought is not depressing. It is, if anything, the opposite of depressing. The universe is richer than we have been able to see. There is more there than has yet been measured. We are not living in a thin sketch of a world. We are living in a dense, deep, mostly hidden one. There is something gentle about this thought when one returns to it after a while. We are not at the center. We are not even most of the matter. We are a small, bright minority in a much larger dark hole. And yet, here we are. We have learned, somehow, in only a few centuries of careful work, that the unseen is there. We have not yet learned what it is, but we know, beyond a reasonable doubt, that it is there. And we keep looking. The dark sector, if it exists, would be older than us, in any meaningful sense. Whatever processes formed it would have unfolded in the first seconds and minutes of the universe, alongside the processes that formed ordinary matter. By the time the first stars lit, the dark sector in these models would already have settled into something like its present form. Its atoms, if it has them, would have formed during dark recombination, well before our own. Its structures, if it has them, would have begun to assemble during dark matter halo formation, providing the gravitational seeds in which our own galaxies later grew. We are, in this picture, a kind of late-arriving guest, building visible things on top of a vast, invisible scaffolding. It is humbling in the right way, the kind of humility that does not diminish us, but expands the space around us. Now let us think, for a while, about the quietness of it. This is one of the things I want to dwell on tonight. The strangeness of how quiet the dark sector must be, by the standards of the physics we know. In our world, when a region of space contains energetic charged particles, those particles emit radiation. The radiation propagates outward, sometimes for billions of years, eventually arriving at our telescopes. We see it, we can read its spectrum, we can deduce from its colors what kind of atoms produced it and at what temperature and density. The visible universe, in this sense, is loud. It is constantly broadcasting itself, in light, across vast distances. We are surrounded by signals. The dark sector, even if it has all the structure we have been discussing, does not broadcast any signal we can pick up. It's dark photons, if they exist, that propagate within the dark sector, not into ours. Its dark stars, if they exist, shine in dark light. Its dark cosmic background, if it exists, glows quietly at frequencies we have no instruments to detect. The whole sector, in our picture, is silent. Not because nothing is happening, but because nothing is happening to us. There is a kind of cosmic loneliness in this image, but also a kind of cosmic dignity. The dark sector does not need our attention to exist. It has been there all along, doing whatever it does, without ever needing to be seen. It will continue, whether or not we ever discover it. It would have continued, in the same way, if no one had ever been born to wonder about it. It is, in a sense, the part of the universe that asks nothing of us. I sometimes find this restful when I think about it for a long time. The bright universe, the stars, the galaxies, the bodies, the cities, the conversations is busy. It is constantly producing signals, and the signals are constantly arriving, and each of them seems to demand something of us. Read me, notice me, respond. The dark universe makes no such demand. It is simply there. It does not ask to be seen. It does not ask to be understood. It does not even ask to exist. It only does. That is a kind of presence I do not know any other word for. If the dark sector is structured the way the most Baroque hypotheses suggest, there might be, somewhere, in some corner of it that overlaps with this room or this galaxy or this corner of the cosmic web, a small, quiet, self-organized region made of dark gas, cooling slowly, contracting under its own gravity, doing something that we, with the most sensitive instruments we have ever built, cannot detect. It would not glow. It would not warm anything. It would have its own internal life in a way, and we would have no idea. This is, of course, only an idea. The dark sector might be much simpler. The dark sector might have no internal life at all. The dark sector might consist of one species of particle drifting unstructured through halos, and that is all. We do not know, but the possibility is not small. It is taken seriously. Papers are being written. Simulations are being run. People, at this very moment, in offices and lecture halls and cold underground laboratories, are working on the question of what the invisible part of the universe might be doing. It is something to lie quietly with. The thought of all that work, the thought of all that patience, the thought of all that not knowing, slowly taking shape into something a little better understood, year by year. Now let us walk for a while along a different path. Suppose that the dark sector exists, and suppose that it has its own forces, and suppose that some fraction of it has cooled and condensed into structures. Suppose, further, that those structures evolved over the same 14 billion years that the visible universe has been evolving. What might they look like? This is a question that, in the literature, is approached only tentatively. Most papers consider only the early stages of structure formation in the dark sector. How the linear power spectrum is modified, how acoustic oscillations propagate through the dark plasma, how the smallest dark halos are suppressed or enhanced compared to the visible case. The later, more developed stages, what the dark sector might look like today, after billions of years of evolution, are largely unexplored because the simulations needed to follow them are difficult and expensive, and because the parameter space of possibilities is enormous. But there are simulations. A recent series of papers, done by a team using the Gizmo simulation code with FIR-2 galaxy formation physics, has explored what happens in a Milky Way-like galaxy if a small fraction of the dark matter, perhaps around 6%, is dissipative atomic dark matter. The result, in some of these simulations, is the formation of a thin, rotating dark disk, embedded inside the visible galactic disk, with its angular momentum closely aligned with the stellar disk. The properties of the disk depend sensitively on the parameters of the dark sector. The dark masses, the dark coupling constants, and the temperature of the dark sector relative to the visible one. In some parameter ranges, the dark disk is thin and dense. In others, it is broader and more diffuse. In all cases, It contributes to the gravitational potential of the galaxy in a way that, in principle, could be detected by sufficiently precise observations of stellar motions. The simulations are exploratory. They do not predict that a dark disk exists. They explore what it would look like if it did, and how its existence might be tested. I find these simulations, at the level of the imagination, very moving. A cold, slow, methodical computer working through the dynamics of a hypothetical universe, asking what an unseen world would look like if it followed certain rules. The world it imagines might or might not be the one we live in. The question it answers is not about the real universe, but about the space of possible universes. And yet, somehow, in working through that space, we learn a little about our own. We learn what is consistent. We learn what is excluded. We learn what we could detect if we knew how to look. The dark disk of the simulation rotates slowly in the dark. The visible disk rotates above and within it, full of stars. Neither knows the other is there. Both are bound by the same gravity. Both have been turning for billions of years. Both will continue to turn for billions of years more. In the simulation, of course, no one is watching from inside the visible disk to wonder about the dark one. In the actual universe, if such a disk exists, we are. We are looking up every clear night at our own bright disk arching across the sky, and we are wondering whether beneath it there is another parallel made of a different kind of substance, hidden from view. We do not know. We may know eventually. The Vera C. Rubin Observatory, which began operations in late 2025, will, over the coming decade, produce a vast new map of the dark matter distribution in the universe by careful study of weak gravitational lensing on enormous samples of galaxies. The Rubin Observatory is named, of course, after Vera Rubin herself, the astronomer whose galactic rotation curves first established the dark matter problem in its modern form. There is a quiet justice to that. Whether or not the new survey finds evidence for any of the dark sector hypotheses we have walked through tonight, it will, year by year, narrow the dark a little further. That is the work of physics. That is the work of any honest inquiry, to narrow the dark slowly until what remains is small enough to see. We are in the middle of that work now. We will be in the middle of it tomorrow. We will be in the middle of it for a long time. There is no rush. There is nothing here that needs to be hurried. So now let us return to the central thought experiment of the night and turn it over once more in the hand. The question was, what if the dark matter has its own physics? What if the unseen part of the universe is not a single, simple, drifting particle, but a whole hidden world with its own particles and forces and structures? In the literature, the answer is, it might. It is one of the live possibilities. It has not been confirmed. It has not been ruled out. The strongest version of it, a fully mirrored sector, with its own complete copy of all known physics, is constrained, but not impossible, in modified forms. The intermediate versions, a small dissipative subcomponent of dark matter, or a dark sector with its own atoms and chemistry, but different parameter values, are alive and being studied. The simple version, just one shy particle with no internal structure, is the default in most calculations, but is not preferred over the alternatives by any compelling evidence. We do not know which picture is right. We may not know for a long time. But the question is taken seriously, and it is not going away. There is a famous piece of advice given by physicists to themselves and to each other when they are trying to think clearly about the limits of what they know. The advice is, do not confuse the absence of evidence with the evidence of absence. We have not detected dark matter directly in any of its proposed forms. This does not mean it is not there. It only means we have not yet found it. The space in which it might be hiding is still, even after decades of searching, very large. Our instruments are sensitive, but the sky is sensitive too. The universe has been here for a long time. It is not surprising that some of its features take more than a few human generations to come into focus. In the meantime, the picture grows slowly. The simple guesses retreat. The richer ones advance. The frontier, where the hypothesis meets the data, moves a little, year by year, toward whatever is really there. It is one of the good aspects of being alive in this particular moment of physics that we get to watch this process happen. The shift in the way physicists talk about dark matter between, say, 1990 and now is real and significant. In 1990, the WIMP was the answer. The conversation was about how to detect it. Now, the conversation is about what to do if it is not there. It is about hidden sectors, and dissipative subcomponents, and ultralight axions, and primordial black holes, and dozens of other possibilities, each of which is a small, careful hypothesis with its own observational consequences. This is what learning looks like when the thing being learned about is hard to learn. I want, before we drift further, to come back to a simple idea. One that I think is worth holding on to even if much of the rest of the night fades. The simple idea is this: most of the universe does not look like us. Most of the universe is not made of the things we are made of. Most of the universe does not interact with light. We, the visible part of the cosmos, the part that includes stars and bodies and conversations, are a small, bright, particular kind of thing, set against a much larger, much darker, much quieter background. This is not, I think, a sad fact. It is a fact about scale. We are not the whole picture. We never were. The picture is bigger than we are. The picture has always been bigger than we are. It is bigger than any one of us, and bigger than all of us together, and bigger than every civilization on every world that has ever or will ever wonder about it. When you lie awake at night and think about dark matter, if you ever do, you can think of it like this: there is more there than what you can see. There has always been more. The universe is full of substance you cannot touch, animated by forces you cannot feel, possibly organized into structures you cannot detect. It is all around you, drifting through the room, drifting through your body, drifting through the planet, drifting through the sun, drifting through the galaxy, in numbers that it would take all night to count. It is not a frightening thought, not at least the way I mean it. It is a thought about how much company there is in the apparent emptiness. It is a thought about how much room there is in even a small part of space for things to be happening quietly on their own. The dark, in this sense, is not a void. The dark is full. Let us walk on. Before we walk on, though, let me return for a moment to one of the simplest images of the night, because I would like to lay it down again with you and see if it can quietly settle. The image is the room you are in right now and the dark matter that is in it. There is dark matter in the room. There has to be. The local density of dark matter near the sun, as best we can measure it, is around 0.4 of a gigaelectronvolt per cubic centimeter. Give or take. That number sounds like nothing when said quickly, but it means that the room you are in contains a small but non-zero quantity of dark matter, drifting through it constantly, all the time. The dark matter does not stop at walls. It does not slow down at windows. It does not gather in the corners. It simply passes through in numbers that depend on what kind of particle it is, but in any case, in numbers great enough to be there at every moment, in every cubic inch of the air you are breathing. The dark matter passing through your body is not, as far as anyone has been able to detect, doing anything to you. It is not heating you. It is not exerting any sensible force. It is not, in any way, interacting. It is only present. It has gravity, and the gravity is far too small to feel, but the gravity is, in principle, there. You and the dark matter share the room, and neither knows the other is there. If the dark sector hypothesis is right, the picture is even fuller. The room contains not just one kind of dark matter particle, but possibly several. It contains, possibly, dark photons exchanged between dark particles in tiny dark interactions that our instruments cannot register. It contains, possibly, the very faint glow of a dark cosmic microwave background, present in the room as it is present everywhere, pressing in at the same brightness it has had for billions of years. It contains, possibly, the trailing edge of a thin dark disk that runs through the plane of the galaxy, slipping through your bedroom on its slow rotation around the galactic center. None of this can be felt. None of this can be heard. None of this changes anything in the visible world tonight, but it is, possibly, all there. The room in this picture is fuller than it looks. The fullness is a quiet fullness. The fullness asks nothing. It is something to lie quietly with before sleep. The thought of how full the empty space is. The thought of how much company is in it. There is no need to settle anything tonight. There is only the long, slow work, somewhere far away, and the long, slow turning of the dark, and the small, bright corner where we live, and the breath in the quiet room. There is a further thought experiment, and we can spend some time with it now, since the night is long and there is no need to hurry. Suppose the dark sector exists, and suppose that one of the more elaborate versions of it, a mirror sector, or an atomic dark matter sector with its own chemistry, turns out to be correct. Suppose that, in some far future, we develop instruments delicate enough to pick up the faint kinetic mixing between ordinary photons and dark photons, and so to detect, for the first time, a clear signal from the dark world. What might we learn? We might learn, first, that the dark world has its own history, its own version of the recombination epoch, its own version of the first formation of bound atomic states, its own dark cosmic microwave background. We might learn what its temperature was in those early times, and how that temperature compared to the temperature of our own plasma. We might learn whether the dark sector and the visible sector had any thermal contact in the very early universe, or whether they have been thermally separated since the beginning. We might learn, second, that the dark world has its own structures, its own halos, possibly its own disks, possibly its own substructures, smaller than what visible matter alone produces. We might be able to map, by gravitational means, the distribution of these structures around our own galaxy. We might find that the Milky Way has a dark disk after all, embedded in our own. We might find that it does not. We might learn, third, that the dark world has its own evolution, its own slow, quiet processes unfolding alongside ours. Its own dark gas clouds are condensing, perhaps, into dark, dense regions. Its own version of complexity, parallel to but distinct from our own. Or we might learn that we were wrong about much of this, and that the dark sector is, after all, simpler, that there is just one particle, drifting in halos, with no internal structure to speak of. That would also be useful to know. The narrowing of the dark would have continued. The simple picture would have survived another round of testing. The rich picture would have been retired as a beautiful idea that did not, in the end, describe our universe. Either result would be progress. Either result would be a kind of completion. Neither would feel, I think, like an ending, only like a settling. What we would not learn, even in the most optimistic case, is the full nature of the dark sector. Even if we detected dark photons tomorrow, we would still have only a glimpse. The further details, the structures, the chemistry, the evolution, would take many more decades, perhaps centuries, to fill in. We are at the beginning of this, not the middle. The middle is far away. The end may not be in any particular human lifetime. That is fine. The work is generational. It always has been. The astronomer who first wondered, in the 17th century, what kept the planets in their orbits, did not live to see the full development of celestial mechanics. The first physicist to wonder, in the 1800s, what light was made of, did not live to see quantum electrodynamics. The first physicists to wonder, in the 1930s, why the galaxies moved the way they did not live to see, and may never see in their successors' lifetimes, the full answer to the question of dark matter. We are part of a long chain of wondering. We are not, individually, expected to finish. It is enough to wonder. It is enough to add a little to the pile. It is enough to leave the question, slightly clearer than we found it, for someone in the next generation to inherit. That is what the people in the cold rooms underground are doing. That is what the people running the simulations on the supercomputers are doing. That is what the people writing the theoretical papers, in their offices, with their coffee growing cold, are doing. They are leaving the question slightly clearer than they found it, day by day, year by year, and the universe in its dark majority is letting them. Slowly, patiently, without any apparent objection. The hour is perhaps getting late. We have been walking for a long time in the dark around a problem that does not move. We have noticed, by feel, several possible shapes it might have. None of them is certain. All of them are, in some sense, beautiful. The walk is not finished. The walk is never finished. But for tonight, let us begin to slow further. Let the breath slow. Let the eyes, if they have not already, begin to close. There is, in the dark sector hypothesis, a particular kind of consolation that I want to offer before we drift too far. The consolation is this: if the dark sector exists, and if it has its own internal life, then the universe is not as quiet as it seems. It only seems quiet because the loud parts of it are not loud to us. Somewhere, possibly everywhere, in the same space we live in, things are happening in ways we have no instruments to register. The cosmic microwave background continues to glow, faintly, in our world. In another world, perhaps, a parallel background glows, faintly, beside it in the same space. Stars do not form in the dark sector in most of the standard models, but other things might. Slow, dim, hidden things, going about their business, without ceremony, without our attention. We are not alone in our little corner of the cosmos, even if we never meet a neighbor. The space around us is full of unseen substance, undergoing processes we cannot follow. This is not a horror. It is a kind of company. It is the company of the unknown, the unmeasured, the patient. It is the company that waits for whoever, eventually, learns to listen. We will not learn to listen tonight. The instruments to do so do not yet exist, but the listening has begun. The first sensitive enough detectors are being built. The first careful surveys are starting their work. The Rubin Observatory has begun its long survey of the southern sky. The next generation of liquid xenon experiments is being prepared. The next generation of axion haloscopes is being calibrated. The next generation of cosmic microwave background experiments is being designed. We will, in the coming decades, hear something. Or we will hear silence more clearly than before. Either way, the picture will sharpen. We will not see it sharpen all at once. It will sharpen the way pictures sharpen at dawn, slowly, almost imperceptibly, until at some point we look up and the whole landscape, which we had not realized was clarifying, has become clear. The dark, by then, will have become the next thing we know. For now, though, it is still dark. The sky outside is dark. The room around you is dark. The universe, in its dark majority, is dark in the older, more original sense, full of substance, only some of which we can see. There are particles drifting through this room, in numbers too large to picture, that no human instrument has ever caught in the act of doing anything. They are passing through your hand, your chest, your eyes, the wall of the building, the rocks beneath the foundation, the iron of the planet's core, on the way to nowhere in particular. They have been doing this since before there was a planet. They will be doing this long after there is no planet. They do not know we are here. They do not need to. This is the part of the night where the careful explanation begins to dissolve, and the older feeling underneath it starts to come up. The feeling of vastness. The feeling of being a small, bright thing in a much larger, much dimmer one. The feeling of sleep begins to gather, like a tide, around the edges of the room. There is nothing you need to do. There is no equation to remember. There is no theory to choose between. You can let it all go. The physicists will keep working in the morning. The detectors will keep running. The universe will keep turning, with its mostly invisible substance, in the way it has been turning for 14 billion years. The mass that holds the galaxies together is still there, doing its quiet work. The Milky Way is still spinning slowly around its dark halo. Andromeda is still drifting toward us, on a collision course 4 billion years long. The Coma Cluster is still, somehow, holding itself together, as it has been for as long as it has existed, on the strength of a substance Fritz Zwicky first noticed almost a century ago, and that we still have not named. If the dark sector hypothesis is correct, there is, perhaps, a parallel disk of dark atoms, lying in the plane of our galaxy, turning at the same rate as the stars, contributing quietly to the gravity that keeps the spiral arms in place. We do not know if it is there. If it is, we will not see it tonight. We will not see it tomorrow. We will see it, if at all, only after many more years of careful, patient, undramatic work, by people who are, at this moment, asleep themselves, in beds in many countries, dreaming whatever physicists dream when they are not at work. The dark waits. It has waited a long time. It is not in any hurry. Outside, the sky is whatever it is, clear or cloudy, or partly the one and partly the other. And behind whatever is visible, the dark matter is there, holding the larger picture in shape. You do not need to see it. You do not need to know what it is. You only need to know, if you want to, that it is there, that the universe is fuller than it seems, that the dark, in its way, is full. The numbers, one more time, in case they are restful. About 5% of the universe is the matter we know. About 27% is dark matter. About 68% is dark energy. Of the dark matter, we do not know how it breaks down. It might be one particle. It might be many. It might have its own forces. It might have its own light. It might have its own chemistry. The investigation continues. There is time. There is always time. Let your thoughts begin to slow. Let the picture lose its sharpness. Let the names of the candidate particles drift away. WIMP, axion, atomic dark matter, mirror matter, dark photon, dissipative dark matter. They were only words in the end. They were our best guesses about something we have not yet seen. The thing itself, whatever it is, does not need our words. It will be itself, regardless of what we call it. The galaxies are turning. The dark halos are holding them in shape. The cosmic web stretches across the visible universe, made mostly of substances we cannot see. The cosmic microwave background continues to glow, in light that has been traveling for nearly 14 billion years, in a faint, warm pattern that tells us, when we measure it carefully, that the universe is mostly something other than us. Somewhere, perhaps in the dark sector, if it exists, a parallel pattern glows in light that no one in our world will ever see. It has been glowing since the universe was very young. It will continue to glow until the universe is very old. It does not need to be seen. The universe is full of things that do not need to be seen. The bedroom around you is full of them. They are passing through quietly on no particular errand, having no particular concern with you or with anything in your life. They will continue after you have closed your eyes, after you have fallen asleep, after the room is silent except for the faint sound of breathing. There is nothing here that needs to be done. There is no question to answer. There is no theory to choose. The physicists will keep working in the morning, and so will the universe, and so will the dark, in its long, patient, mostly hidden way. The galaxies will keep turning. The halos will keep holding. The cosmic background will keep glowing in our sky and perhaps in another parallel sky we cannot see. The investigation will continue, slowly, year by year, as it has for nearly 100 years, and as it likely will for 100 more. There is no hurry to any of this. There is only the long, slow work, and the long, slow turning of the dark, and the small, bright corner where we live, and the breath, slowing further in the quiet room. There is a thought I want to leave with you before we drift the rest of the way down. It is not a conclusion. There are no conclusions tonight. It is a small thought, a quiet one, and it is something like this. For most of human history, when people looked up at the night sky, they did not see what we see. They saw a dome of stars, fixed at some unknown but apparently small distance overhead, with the moon and the planets wandering among them. They did not know that the stars were suns. They did not know that the suns had planets. They did not know that the night sky was the inside of a galaxy, viewed from one of its arms. They did not know that the galaxy was one of billions, scattered through a universe so large that light itself takes millions or billions of years to cross between its parts. The picture has expanded slowly, generation by generation, with each new instrument, each new measurement, each new piece of careful work. Each expansion of the picture has, in some way, made the visible universe smaller, not smaller in absolute terms. The universe has only grown in our understanding, but smaller relative to what it sits inside. The Earth, once thought to be the center of everything, became one planet among several. The Sun, once thought to be the unique source of light, became one star among many billions in our galaxy. The Milky Way, once thought to be all there was, became one galaxy among billions in the observable universe. Each step, we have learned that what we can see is a smaller fraction of what is. The dark matter discovery is, perhaps, the next step in this slow shrinking of the visible. We have learned that what we can see, the bright matter, is only about 5% of the total. The other 95% is something else. Something we do not yet know how to look at, made of substance we have not yet learned to handle. The bright universe in this picture is not the universe. The bright universe is a small, bright minority of it. The picture has expanded again. The visible has, again, grown smaller relative to what surrounds it. I do not think this is a sad story. I think it is the truer story. We have gotten slowly a little closer to the actual size of things. We have learned to be honest about how much we do not see. We have learned that the world we inhabit is layered into things we can touch and things we cannot, and that the things we cannot touch are by mass, by structure, by everything except our own attention, the larger part. We are not the center. We were never the center. The center, if there is one, is much further out and much harder to find than we used to imagine. If the dark sector hypothesis is right, the next step in the picture, the next expansion, has already begun. We have started to consider that the unseen part of the universe might not be one simple thing, but many. That it might have its own structure, its own forces, its own history. That in some way, our visible cosmos is one layer of a thicker, more complicated, mostly invisible cake. We will not confirm this in any single moment. We will, perhaps, slowly accumulate enough indirect evidence over the coming decades that the consensus will shift, or we will not. Maybe the dark matter will turn out, after all, to be one simple particle, and the dark sector ideas will be quietly retired. We do not know. What I want to leave with you, before we drift, is the feeling that this is a good kind of not knowing. It is the not knowing of standing at a fence, looking out across a landscape that we have just begun to map. We can see further than people used to see. We cannot see all the way. The edges of what we know are real edges, and they are not always disappointing. Sometimes they are simply the boundary between what we have learned so far and what is still ahead. Tonight is, in a small way, a moment at that fence. We have stood here for a while. We have looked out in the soft evening light at the strange shape of the dark country beyond, and we have noticed some of its features and named some of its possible inhabitants, and accepted that we do not, yet, know which of them are real. Now the light is fading. The features in the distance are getting harder to see. It is a good time to step back inside and rest. The fence is still there. The country is still beyond it. We will come back to look again tomorrow, or the day after, or the year after that. We will, sometime, take another step out into it when we have built the right boots, the right tools, the right instruments. The walk is not over. The walk has barely begun. For now, for tonight, the walk is paused. The sky is dark. The room is quiet. The dark matter, whatever it is doing what it does in the way it has been doing it for billions of years, without any need from us. The galaxies are turning. The halos are holding. The cosmic web stretches across the night, mostly unseen. The galaxies are turning. The halos are holding. The cosmic background continues to glow in our sky, and perhaps in another parallel sky we cannot see. The investigation will continue, slowly, year by year, as it has for nearly 100 years, and as it likely will for 100 more. There is no end to this. There is only the long, slow work, and the long, slow turning of the dark, and the small, bright corner where we live, and the breath, slowing now, in the quiet room. There is more there than what you can see. There has always been more. There will always be more. The dark is not empty. The dark is full. And the universe will still be turning when you wake.